morning, students. Dear all, welcome to today's session, Spur Gear Design, Part 1, Beam Strength of Spur Gear Tooth. Myself, Professor Kushare, Mechanical Engineering Department, Kekewag Institute of Engineering Education and Research, Nasik. Today we are going to discuss beam strength of gear tooth and how to find out beam strength of spur gear. Learning objective of today's session is explain beam strength of gear tooth. Today we are going to discuss this point which is related to spur gear. In earlier session we have discussed the classification of gear, force analysis of the gears. Now let us see beam strength of spur gear tooth. You know very well the analysis of bending stresses in gear tooth was done by Mr. Wilfred Lewis in his paper. He presented the investigation of the strength of gear tooth at Engineers Club in 1892. And even today, Lewis considered as the basic equation in the design of spur gear. In Lewis analysis, the gear tooth is considered as a cantilever beam. You can refer this figure, you will find the gear tooth, which is considered as a cantilever beam by Mr. Lewis. So you will observe here, this is the gear tooth, which is subjected to tangential force PT. Again here, tangential component PT, which causes the bending moment about the base root, is also uniformly distributed. Then this is the B is the width or pitch width of the gear tooth or spur gear tooth. Now we are in beam strength of gear tooth. Lewis equation that we are going to derive, and it is based on some of the assumptions. Let us see the assumptions made here in Lewis analysis while deriving his equation. The assumptions made in Lewis equations are: the first one, the effect of the radial component PR, which induces compressive stresses, is neglected. You know very well, as per our earlier discussion, spur gear is subjected to tangential as well as radial load. The effect of radial component, which induces compressive stresses, which are neglected here in Lewis equation. We are not taking care of this. We are assuming it compressive stresses are not present. But in actual practice, you will find because of this radial component or a load, it induces compressive stresses, but it is neglected here in Lewis equation. This is first assumption. Second assumption is the tangential component PT is uniformly distributed over the face width of the gear. Face width of the gear, refer this figure, earlier figure, you will find here, this is the face width which is generated by B, and here PT which is shown, the PT which is uniformly distributed. Look at this, it is uniformly distributed. And it is assumed again here in Lewis analysis or in Lewis equation. Now again you will find here, what is the second assumption? The tangential component PT is uniformly distributed over the face width of the gear. But when it is possible, it's possible only when gears are rigid and accurately machined. Try to understand. Then third assumptions made in Lewis equation is, that is, effect of stress concentration is neglected. During the dynamic load conditions and during practical, in the practical application, you will find the effect of stress concentration plays important role. But to make the analysis simple one, the effect of stress concentration is neglected. And fourth assumptions, it is assumed that at any time only one pair of teeth is in contact and it takes the total load. But you know very well, for a proper meshing of the pinion as well as the gear or gear pair, contact ratio should be always greater than 1. But here one pair of teeth is in contact, it is assumed, but you will find along with this one, some part of the other pair is also in contact. In theory of machine already you are studied this part. This is the fourth assumption which is made in Lewis analysis or in Lewis equation. Now let us see how to derive the equation. So before that, look at the figure here. I have taken is from V. Bandari's book here. This is the gear tooth. Here XX is the section. It is the weakest section of the gear tooth. This is the weakest section of the gear tooth, where there may be possibility of failure of the gear. Try to understand. Look at this again here. Here you will find this is the gear tooth. Again, PR is the radial component, PT is the tangential component, and again you will find here this is the resultant component of the gear forces which acts in this direction here. Try to understand. Then what is going to happen? So you will find the cross section of the gear tooth varies from free end. Free end means from this end up to this, that is the fixed end. It varies. Look at the diagram. You will find it's a varying. It's not like this vertical like a rectangle or like a square. It's a varying one. And because of that, in the analysis, we should have a beam of uniform strength. And to have a beam of uniform strength here, parabola is constructed within the tooth profile. And this parabola, which is shown by dotted line here, which is constructed here. Look at this parabola. This is very important, this parabola. Because of this parabola, what is going to happen? So we will get the beam of uniform strength. That's why this parabola plays important role. Otherwise, you will not get a uniform strength of a gear to try to understand. That's why parabola is constructed. And again, stress at any cross section of the gear tooth or parabolic beam is uniform and same. That means for this parabola, we will obtain the uniform strength for the gear to try to understand. That's why parabola is the important one. Parabola is important one. Again here, if you are going to look for this, the parabola here up to this portion, so you will find at XX, it's a wicked section of the gear tooth where the parabola is tangent to the tooth profile. Parabola is tangent to the tooth profile. At this section, suppose what we have to do, we have to carry out the analysis at this section. At this section, bending moment MB is equal to bending moment. If we are going to find out bending moment at section XX, what is the relation? Simple. PT, which is going to act here, tangential force, at a distance of r height h. So we will get bending moment at section XX. Therefore, MB is equal to PT into H. Again here, to find out the bending stresses, what is the simple relation? MB sigma B is equal to MB into Y upon I. To find out bending stresses, so first of all, we have to find out MB, but here MB is equal to P2 into H. The Y is also required and I is also required. So first of all, let us find out Y and I. How to find out it? Now here I is equal to 1 by 12 BT cube. Look at this. It's a neutral axis. And again here the cross section, which is at a section XX. And this is B. This is B. Now, what we have to do? We have to find out the Y at neutral axis. If we are, this is the thickness here T. So what you will get this distance from the neutral axis, you will get T by 2. Therefore, Y is equal to at XX T by 2. And we know the I, that is BT cube by 12. So what we have to do to find out sigma B is equal to MBY by I, we have to substitute these values MB, I and Y. Let us see. After substituting the values here by using the simple equation, That is MB is equal to MBY by I is equal to. What is MB? I have already discussed and told you that is PT into H. What is Y? Y means T by 2. This Y means T by 2. MB means P T into H. And what is I? BT cube by 12. You know very well. After substituting all these values, you will get sigma B. What is the next step here? So what you have to do? You have to rearrange the terms here. After rearranging the terms, find out PT is equal to. So what you will get? PT is equal to V into sigma B into T square upon 6H. Rearranging the terms. Here sigma B is equal to, so you can find out PT. So you will get PT is equal to B into sigma B into in bracket T square upon 6H. This term. Then multiply to the numerator and denominator of the right hand side by M. M means module. You know module very well. We have already discussed these things. So multiplying numerator and denominator of right hand side by M. So what you will get? The PT is equal to, what you will get? PT is equal to MB sigma B in bracket T square upon 6HM. What we have did here, it is multiplied by M, and here also it is multiplied. That means multiplying or multiplied by M to the numerator and denominator. If you are going to cancel, you will get the same equation. Try to understand. Then here, what you have to do after multiplying here, what the terms, what is the modification? The PT is equal to MB sigma B in bracket T square upon 6HM. And this term T square upon 6HM is known as Lewis form factor Y. And defining this factor, so we are going to state here Y is equal to T square upon 6 into H into M. So we have introduced here one factor, that is Lewis form factor Y. This is Y, and Y is equal to T square upon 6HM. Therefore, you can replace this term by Lewis form factor Y. So what you will get? Here you will get PT is equal to M into B into sigma B into Y. Try to understand. And now look at this equation. It's very important one. Now PT is equal to M into B into sigma B into Y. What is M? Module. B means width here. Sigma means bending stress, and Y means Lewis form factor. But if you are going to refer this term Lewis form factor, is having the T thickness, then H height, M is the module. That means Y depends on THM. But for a meshing pair teeth, you know very well, this H and T are same for a pinion as well as for the gear. But what's about the module? Module is also same for the pinion and gear. But to have a constant module for pinion or same module for pinion and gear, if it's not a constant, so what would happen? There is no proper engagement of pinion with gear. Try to understand. And you know very well, TP or the P circle diameter is equal to M into ZP. Simple expression. That means M is equal to D by Z. That means module depends on Z. That is number of teeth on pinion or a gear, and number, that is PCD, P circle diameter of the gear or a pinion. Try to understand. Therefore, module depends on PCD and number of teeth. Therefore, to maintain this constant for a pinion, same for a pinion and gear, we have to make the arrangement in the values of Z and PCD. Then and then it's possible to have a same module for pinion and gear. And if it's same, that means there is a proper engagement. Otherwise, it's not possible to have a proper meshing of pinion with gear. Try to understand. Module of pinion and module of gear both are same. Okay, that means if T is same, H same, and in module is also same, but module is defined in terms of PCD and Z. That means Lewis form factor depends on this PCD and Z. Z means number of teeth. Therefore, if you are going to select a Lewis form factor, we have to refer this. Z means number of teeth on pinion and number of teeth on gear. It decides the Lewis form factor. Try to understand. It's okay. Then second thing, we have derived these terms MB sigma B into Y. So we will see the one module with sigma B bending stress and Lewis form factor. I already told about this Y. Then again here, when this we are going to increase this PT, what would happen? The stress is also going to increase. Try to understand. And when this stress, we stress the sigma B bending stress, or when this stress reaches the permissible magnitude of bending stress, the corresponding force PT is called beam strength. That means, look at this here. Once again, I will repeat. As we are going to increase the PT means tangential force, this sigma B is also going to increase. And when this sigma B or stress reaches to permissible magnitude of bending stress, permissible magnitude of bending stress means after that there may be possibility of failure of the gear tooth, or when the stress value exceeds, then failure of the gear tooth may occur or happen. This value. Therefore, as the PT we are going to increase, sigma B is also going to increase. And when it reaches to this permissible magnitude of bending stress, the corresponding this PT is known as SB or beam strength. Therefore, what we have to do? We have to replace this PT by SB. So let us see. That's why I have replaced this PT by SB. Therefore, SB is equal to M into B into sigma B into Y. Try to understand. Therefore, I am going to define beam strength of spur gear here is the maximum value of what? PT. And when it reaches to maximum value, then and then this stress is also going to increase because of the PT max. And when it reaches to the permissible magnitude of bending stress, then corresponding PT we are going to say is a SB. Therefore, beam strength SB is the maximum value of what? Tangential force. And that the tooth can transmit without bending failure. So simply, how we are going to define SB? The SB or beam strength of spur gear tooth is the maximum value of tangential force that tooth can transmit without bending failure. This is the proper definition of SB. Proper definition of SB. Try to understand. Therefore, PT is replaced by SB. So you can say this is the Lewis equation. SB is equal to MB sigma B into Y. Okay, I hope you understood this. Now let us see. There are some terms here. M module B with sigma B. What is sigma B? Sigma B is the bending stress. Sigma B is the bending stress. And what is Y? Lewis form factor. Now, you know very well, we have already discussed about the B, then module. So now today we are going to discuss these two terms, sigma B and Y. Sigma B and Y. Let us discuss one of first term, sigma B. Now, sigma B is the bending stress. Now here, it's a permissible bending stress up to the, the when PT is maximum, up to which that gear tooth can sustain without bending failure. Now here, look at the first figure, you will find here, suppose this is a driving gear, it's a idler gear, it's a driven gear. If it is going to rotate in clockwise, it is going to rotate anti-clockwise. When it is anti-clockwise, again it is driving in clockwise. So you will find, because of this position here, driving and driven gears, what is going to happen? And when it is going to engage with the idler here, so you will guide the stress intensity or stress here, which is shown here as by sigma max. And here, after one revolution, what is going to happen? Again here, when it is going to rotate, you will find it is idler, through idler, the driving gear rotates driven gear. So you will find again, after one revolution, it the stress limit or magnitude is also sigma max for driving and driven gears. And here, it is going to happen after one revolution. If I am going to construct again here After one revolution, the same, the stress magnitude you will get here on this stress time diagram. That means these stresses are repeated stresses. These stresses are repeated stresses. Try to understand. It's a fluctuating stress. Therefore, I am going to make a statement. Tooth of the gear subjected to fluctuating bending stress, repeated stress. Then second case, if this driving and driven gear subjected to repeated stress, so we have to find out. Already we studied in DME 1 how to find out this mean of this sigma mean and sigma amplitude. You know very well here the sigma max by 2 and sigma amplitude sigma max by 2 here. So you will get the magnitude of mean and sigma stress amplitude. Sigma m means mean, MEAN, and amplitude 1/2 of sigma max. But again, look here for the idler gear, when it is subjected, when it transmits, when comes in contact with the tooth of the driving gear, what is going to happen? So you will get the stress on the stress time diagram here. You will get the sigma max here. Again, when it is going to rotate after this, so you will get the half revolution. Again, you will get the sigma max because it tries to rotate the driven. And after that, again, in driven, again, you will get the same magnitude sigma max and it repeats. So you will find here nature of this the stresses which observe it's a reverse stress. The first, second, third, fourth, reverse. It's a reverse one. Try to understand. And you will find this for this idler gear. It's a subjected to reverse stress, or in other terms, I am going to say teeth of the idler gears are subjected to stress in both the direction. Both the means from driving and driven, and these stresses are called reverse stresses. Try to understand. And therefore, for reverse stresses, how to find out sigma mean? If I am going to consider this a zero line, you know very well this line on time. This is sigma mean. The sigma mean is equal to 0. So I have written here sigma mean is equal to 0. And sigma amplitude means it's a sigma max. Therefore, sigma A is equal to sigma max. And if these gears, if tooth of the gear is subjected to fluctuating means repeated or reverse or fluctuating bending stresses, that time what is the criteria? Already you studied in DME1, endurance limits is the criteria, or endurance stress is the criterion which is denoted by SE, and therefore SE is the criteria. Therefore we will see here the maximum bending stress is equal to the endurance limit stress of the gear tooth, and this endurance limit stress of the gear tooth depends on, there are some parameters, you know very well. SE is equal to K into KB into KC into KD into SE dash. So what are the factors or gear tooth? Same parameters. Surface finish of the gear tooth, that means finish factor. Size of the gear tooth, size factor. Reliability, the reliability factor. Stress concentration, KD 1 upon KF. And along with this, two important factors, gears are rotating in one direction or both direction, or gear tools are subjected to stress in one direction or both direction. Based on that, whether it is subjected to reverse or fluctuating stress. Try to understand. And once if it is subjected to fluctuating, then the endurance limit stress of gear tooth is approximately 1/3 of the ultimate tensile strength according to Buckingham. Therefore, I am going to write sigma B is equal to SC. SC means endurance limit is equal to 1/3 of SUT. And therefore, I am going to say sigma B is equal to, or maximum bending stress is equal to endurance limit, that is 1/3 of SUT. 1/3 of SUT. That means if I know SB is equal to M into B into sigma B into Y. So what is the value of sigma B that you have to substitute? That is SUT upon 3. Try to understand. Now let us see the another term, Y, Lewis form factor. I will explain that. I have discussed this term sigma B. Now let us see Lewis form factor. You know very well Lewis form factor. Why? Again, in derivation we have taken t square upon 6hn. You know very well t and h, which remains same for pinion and gear. Module is also same, but module which is defined in terms of PCD and in terms of Z. The model depends on Z. Z means number of teeth on pinion or gear, and D means PCD of pinion or gear. Therefore, Y depends on PCD and Y depends on number of teeth on pinion and gear. Therefore, here I have taken the data from data book. For Lewis form factor for 20-degree full depth involute system, look at Z means number of teeth, Y means Lewis form factor, Z number of teeth, Lewis form factor. For 15 teeth, 0.289, 19 teeth 0.314, 75 teeth point. As the number of teeth increases, value of Y Lewis form factor is also going to increase. Or is more, you can say. Depends on number of teeth, the value of Lewis form factor that we have to take by using this data book or any data book you can refer. So you will get the value of Lewis form factor. But Lewis form factor that we have used here t square by hm, but t is same for pinion and gear. H is also same. Model is also same, but model is defined in terms of d and z. Therefore, y is also depends on z and d. Again here depends on z. Here you will find z 15 to 0.8. As the z increases, the value is also going. Instead of 0.89 is 0.295. This is one thing. Now we are going to discuss one important point. You know very well I have written SB, beam strength SB is equal to what? M into B into sigma B into Y. Now suppose if here in, look at this, suppose this is the pinion, one gear is pinion, second one is the gear, and both are made up of same material. Same material means, so you will find here material is same, means module for pinion and gear same, B is also same, then same material means bending stress that we are going to calculate from SUT by 3. So it is also same, only Y Lewis form factor that we have to find out. And again for a pinion, always gear teeth are less than the gear, and therefore you will find the value of this Y is also low than the gear. Therefore, for same pinion and gear material, Lewis form factor Y is always less for pinion compared with the gear. For that, you can refer this chart. And based on that, we can make the statement here. Therefore, pinion is always weaker than the gear. What is the statement? Pinion is always weaker here, always weaker than the gear. But when same material is used for pinion and gear, so for same material for pinion and gear, pinion is always weaker. I have explained why weaker, because M is same, B is same, sigma B is same, only Y decides. And for pinion, number of teeth are less than the gear. That's why Y value is less, and that's why pinion is always weaker. This is the case. But if pinion and gear are made up of different materials, different means suppose pinion which is made up of plain carbon steel, gears which is made up of alloy steel, then what to do? That time, if I am going to write the same equation, SB is equal to beam strength M into B into sigma B into Y. Again, for a meshing pair, M remains same, B same, only sigma B into Y, because if it is pinion is made up of one material, sigma B is different because SUT is also different. SUT by 3, and here Y number, the Y depends on number of teeth. So therefore, if different materials are used for pinion and gear, the product, this sigma B into Y, sigma B into, it's a into sigma B into Y, it decides whether the pinion is weaker or whether the gear is weaker. For that purpose, what we have to do? We have to determine sigma B into Y for pinion. Based on the material, you can take sigma B SUT by 3. Y depends on It's a Lewis form factor, depends on number of teeth. You can find out this term. And then again, what you have to do? You have to find out sigma B into Y for gear. Again, gear material is different, the SUT by 3 and into Y, number of teeth on the gear. And based on that, find out Lewis form factor or take from this data. So you will get this term and you can check whether the sigma B into Y for pinion is greater or less. And based on that, we are going to decide whether pinion is weaker or whether gear is weaker. I hope you understood this. This is about the Lewis form factor. This is about the Lewis form factor. Try to understand. Again here for different pressure angles, the chart is provided here. Lewis form factor on y-axis, Lewis form factor, number of teeth on x-axis, and I have already told as the number of teeth increases, Lewis form factor value is also going to increase. Now here, look at this chart. This is for what? Phi is equal to 20, pressure angle is equal to 20 degree. Then phi is equal to here 20 degree. And here this line, it goes again in phi is equal to 25 degree. And phi is equal to 14.5 degree. Again here, whether it is a involute profile or a, now here for Iraq, it's okay. For the which type of profile which is used, accordingly we have to use phi is equal to 20 degree. And based on that also number of, if it's a 20 degree, you can select this point, then you will get the Lewis form factor on this vertical line. In this way, by referring to chart also, you will get the values. Otherwise, by using these charts again, what you have to do, some empirical relations are given by some of the persons. Now suppose for a 20 degree pull depth involute system, y is equal to, I am going to write the formula, it's available in many books, 0.484, 484 minus 2.87 upon Z. Now suppose if you would like to find out the Y for pinion, here you have to take ZP, means number of teeth on pinion. If you would like to find out Y for gear, Lewis form factor for gear, you can use ZG. In this way, and then you can use this relation sigma B into Y for pinion, and another one sigma B into Y for gear. And based on that, you can check whether this value is more or this value is more. And based on that, for different materials, when different materials are used for pinion and gears, we have to decide whether pinion is weaker or gear is weaker. In this way, we have discussed the beam strength of the gear tooth by using this equation. SB is equal to MB, M into B into sigma B into Y. We can easily find out the beam strength. And where M is the module, B is the speed, sigma B is the bending stress, that is equal to SE is equal to SUT by 3, and Y means Lewis form factor. And how to select the Lewis form factor? By referring the chart. And when same material is used, pinion is always weaker. When different materials are used, then how to decide which one is weaker and stronger? The sigma B into Y product plays important role. Again, this chart is also given in many reference books. You can refer the chart, but this chart for different involute and pressure angles of tooth profile. Accordingly, we can use these charts. Thank you. Thank you very much. This is about the beam strength of the spur gear tooth. Thank you. I have referred B.B. Bhandari's book, Design of Machine Element, 3rd edition, McGraw-Hill publication. Thank you. If you have any query, contact me at 9890426679 or mail me at pbkushare@kkewak.edu.in. Thank you. Thank you very much.